Hello, everyone. I'm Peter Samoaa, and I'm a PhD student at Chalmers University of Technology. This presentation is for ICPE 2021 regarding my accepted paper, which is about an exploratory study of the impact of parameterization on a JMH measurement results in open source projects. And this work is developed in cooperation with the professor Philipp Leitner, which is my advisor through my PhD. So I'm going to start the presentation talking about the JMH. JMH is an abbreviation for Java Microbenchmark Harness. It's a widely used tool for testing performance critical code on a low level. One of the key features of the JMH is the support for user-defined parameters, which allows executing the same benchmark with the different workloads. An example of a real-life JMH benchmark class from the GC Tools project is provided in the following. So we have a Java class, which is a set ops that define 4 benchmarks implemented in 4 methods carrying at benchmark annotation. In addition, we have 4 user-specified parameters are defined using at param annotation. The method annotated with at setup is executed once at the beginning of the process to set up the necessary tested data. Each of these benchmark instances will then be executed for a number of time, which is the number of iteration in a warm-up, which is going to be ultimately discarded, and also the number of iteration in the measurements. However, a benchmark configured with n parameter with m different values each requires JMH to execute the benchmark m to the power n times. So once for each combinations of the configured parameter value. Consequently, even modest parameterizations leads to a combinatorial explosions of the benchmark that must be executed, hence dramatically increasing execution time. However, so far, no research has investigated how this type of parameterization is used in practice, as well how important different parameters are to the benchmarking results. So that's why ultimately we designed this kind of experiments in order to support the developers in selecting appropriate benchmark parameters, because currently developers set different values for parameters, then run benchmark in order to observe the performance value, and then they change the parameter values and run again the benchmark in order to observe the changes of the performance values. So if we are dealing with a complex benchmark, so this kind of experiments takes a lot of time, a lot of effort, and also a lot of resources in terms of computational resources. If we are talking about the benchmark, that takes a lot of time in order to be executed. So building kind of a solution that's in the fewest number of run of an experiment, the developer can get the most information about the impact of the parameterization or the parameters on the benchmark value through understanding the relationship between those parameters and the performance value. So we start collecting data. So as a common for exploratory research, we employ a purposive sampling on both project and benchmark level. And purposive sampling subjects are selected explicitly based on the preserved usefulness to the study goal rather than drawn randomly from a population. We choose those projects because there are frequently used parameterization in their benchmark. They are well maintained, well known, important in practice. They cover a range of different types of projects. For each of these 5 projects, we manually select 5 to 6 concrete benchmark classes, again using a purposive sampling strategy. So we select benchmark classes that they have parameters, typically multiple, and we suspect that they have a different characteristics due to having a different code structure, different parameters, or even their location in different Java packages. So to collect the data for our study, we built such a tool that repeatedly executes the selective benchmarks with a randomly generated parameter values. So to do so, we manually inspected the selected benchmark classes. So for example, here we have the projects of Eclipse collection that as an example, we pick up those five classes manually based on purpose of sampling. Inside each class, there's a concrete benchmark and there's a parameters that for each class. We have many kind of parameters. So we have metric parameters that hold either integer values or decimal values, and we have a categorical parameters. For both type of metric parameters, we define a minimum and maximum values based on the current configuration of the projects on GitHub, and randomly generate a concrete parameter value through a uniform sampling between the minimum and maximum. For categorical parameters, we simply select randomly from all predefined parameter values. Our initial goal in analysis was to identify how strongly using different parameter values impact and resulting benchmark measurements. To this end, we use a combination of a visual analysis and a feature selection. Visual analysis can let us understand the correlations between the individual parameters and the performance value, whereas the feature selection let us understand the importance of each parameters in a collective level, I mean among all of other parameters on the class, on the same class. So we obtain so many different results, but in this presentation, we give it just a snapshot for a few results. So in 66 combinations of the parameters, of the benchmark and the metric parameters, which constitute like a 40%, we observe that parameters was uncorrelated with the measured benchmark value. So the following figure, a metric parameters, which is the length, does not impact the benchmark result at all. So here the developers can understand that investing in these parameters will not give, let's say, clear correlations or the clear expectation about how the changes of the length values will affect the measurements, right? For the metric parameters that impact the results, the most common relations between the parameters and the measured value in our sample are power law correlations, which we have observed in 42 benchmark parameters combination, which constitute like a 26%. So here, the developers can understand that for the smallest value of the size, right, the measurement can change according to the power law distributions, right? But when we increase the amount of size, the value of the size, the parameter or the measurements will not change at all because here the performance is stable. So understanding this kind of relations will let the developer, right, will let the developer expect the performance value or the measurements regarding the size. In 22 combination, which constitute 13%, we observed that the relationship between the parameters and the measured value cannot be described through a single function, as there are one or multiple discontinuities where the distribution changed. Most frequently, this take the form of the state function. For developers, awareness of this situation is crucial, as there is a little to be gained from executing the benchmark multiple times with a parameter value in the same range. So here the developers can pick up only one value, okay, from each range in order to test the measurement, as for each range, the measurement value is stable, right? Now, after analyzing the impact of individual parameter in isolation, we now assess the relative importance of the parameters in benchmarking classes with multiple parameters, right? So the score here is related to the parameter importance, right? So we rely on impeding feature selection, right? Um, that rely on machine learning or in-sample machine learning model to study or to measure how each parameter is contributes, right? Contributes in the performance value, right? So usually this score refers to the contribution of independent parameters regarding to the dependent parameters, right? As we can see here, there is one parameters, right, that is dominant among of all other parameters, right? So what's the insight that the developer can gain now is that the developer can dedicate most of their time for one parameters rather than the other parameters, right? I mean, most of their time and effort regarding the testing of the parameters. As we have observed, most parameters either do not have an impact on the observed benchmark result at all, or the correlation between the parameter value and the measurements follows fairly predictable curves. Hence, we speculate that, given a sufficient training data, it's possible to infer the performance of the untested parameter combination with high accuracy, without having actually to run the benchmark for this specific parameter configuration or combination. Sorry. This supports what-if analysis and allows developers to reason about the performance of their system in a specific situation. Like, for example, when defining a low-level throughput or response time guarantees. To build this predictive model, we use a machine learning model based on random forest regression. We are dealing with the regression problem because the model will predict the outcome of performance test given a specific JMH benchmark, which is a continuous numerical value. Moreover, since each class has its own set of parameters and benchmark, we will build one model for each benchmark class. So the flow or the learning flow of the model is, for example, we start with this class for these parameters with X class for that has those kind of parameters. We have two parameters that they are categorical. So we need to encode this kind of parameters using one-hot encoding. So once we encode those parameters, the value of those parameters become the features, right? And they hold with the values of 0 or 1 based on their occurrences in the data point that we have. And then we divide the data into two parts. The part for training, which constitute like 80% of the samples that we have, and the part for testing, which constitute 20% of the samples that we have. And then we inject it into the model for training and testing. So when we test the model, again, the results obtained from this is kind of just an example or snapshot from the Eclipse project, Eclipse collection project. So as you can see here, so we rely on R square in order to testify, in order to evaluate the model. So R square is a statistical measure that represent the proportion of the variance for the dependent variable, which is here in our example, the performance value, that is explained by independent variables, which is the features that we present in the previous slides. So as you can see here, we have for most of the classes, all of the classes, we have a high accuracy model. So here we can use the efficient model or machine learning model for predicting the performance value for the untested parameters. So to sum up, through these experiments, we study or we investigate the parameterization of the JMH benchmark on a different level. So on the individual level, we investigate the impact of individual parameters on the performance results, and we found out that 40% of the JMH parameters have no observable impact on the measurement results. And then we rely on the feature selection in order to quantify the importance of different parameters for the benchmark classes with the multiple parameters. And ultimately, we rely on the machine learning model, right, that predict the measurements for the unseen parameterization. Thank you for attention.